And then we know that u0 is also less than r squared. So trivial dipole radius r. So we shall see now that when I do this scaling, the limit function u0 will actually be a homogeneous function. That's the same. Once we have that, then we have probably a simpler proof. Okay, here is a monotonistic function. Again, it's fine. So you remember the functional? This is the functional, basically. The energy functional. If you minimize this, think of R being 1. Think of R being 1. If you minimize this part, you're going to get the PDE. If you have the president is going to be the characteristic function. What I'm doing is, it's called the Weiss monotonistic formula, basically, because your Weiss started using it more frequently. But this type of thinking, this type of monotonistic formula appears in other areas much before, especially in studying harmonic maps. And I think when the former student of Albert Friedman, if I remember the name correctly, was doing actually using this first time, and then independent device was using it, and then but he used it in different versions and applied it much more frequently to other areas, two-phase problems, etc. It's very effective too. It looks like what is also called Holmgren's frequency, or very close to that. So somehow Holmgren's frequency formula would be you divide the whole this guy with this one. If you divide it, that would be called basically Holmgren's frequency formula. So they're related. And yeah. So what you do, you write it like this, and now you want to say, why do we write this? I mean, if you forget about R, so bottom radius is 1. This is the Dirac energy plus the extra term force that we have. And that you minimize this energy, you get a solution to your PD. That PD, basically. U is now negative. And now what I'm doing, I'm balancing it with something. Now I'm claiming that this is going to be bound. The reason for balancing is very important. Because what you think of is, if your solution is homogeneous, what can happen? So think of homogeneous polynomials. You can put anything you want here. But since you're thinking of your function u there, being like r squared, that's homogeneous of degree 2. Okay? So you're expecting it to be homogeneous of degree 2. If it's homogeneous of degree 2, what does it mean? It means u is like r to power 2. If it is homogeneous, we don't know that, but it's homogeneous, that's the best scenario. It's r to power 2. Then you have a 2 here that balances. Then you have the volume, and then n. If u is homogeneous of degree 2, the gradient is homogeneous degree 1. Degree 1 to power 2 is again 2, that compensates this. If it's degree 2, this is degree 4. 4 plus n minus 1, that's n minus 3, n minus, what did I say? Did I say right?
Yes, n plus 3.
4 plus n minus 1 is n plus 3. Yes. So you see that balancing is correct. So the only question here is, why do I add this one? This one again you add because it's homogeneous. You will see that this guy is almost like this guy. And then there is a 2. Actually, we can get rid of this also because, well, it's a computational. Because gradient of, if you take a homogeneous function, you take gradient of the homogeneous function, that would be like x time the function, 2 times the function itself, and that 2 is sort of compensating here. Get 2 to power 2, that's going to be 4, and then you require this to go away. Well, anyway, let me not go into that, but that's a compensation, basically, you have to compensate. So now what you do, you scale. You look at my UR. So what I do, instead of U, I can actually write UR. I scale it. Okay, radical substitution, change of variables. If I write there Rx plus Z is Y, then I can rewrite the whole thing like this. So if Rx plus Z is Y, then this is the way writing. Now you want to prove that this is monotone. When R goes large, W goes large. So how do you do that? There's only one way to take the derivative and prove that the derivative is non-negative. If you're not used to taking derivative of functionals, then just think them as integrals are not there when you take the derivative. So think there's no integral here because you're not doing anything with this. Of course, you have to verify that you can do that inside the integral, but let's say formally you can do that. So you go inside and take the derivative of everything. So if you take the derivative of this function, let me just do one of them. If you have this function, u of r x plus c divided by r squared, and you take the derivative with respect to r. So what's going to happen? This is a function of r, this is a function of r. So you have the derivative of this guy with respect to r as a triangle, okay, and divided by r squared, and then minus 2 times r to the power 3 and u. That's it. So what is the derivative of this in r? It's got to be gradient of u at the point, and then the derivative of this, that's going to be x basically, and then you got r power 2 minus, if I could write it, I'll let me write it like this, minus 2 times. You are divided by r. I can rewrite. If it's homogeneous at degree 2, what do you going to get here? Prove this is 0 if it's homogeneous at degree 2. But if it's homogeneous of degree 2 at the point C, then it means that you can just cancel it and write u of x, and that's going to be 0. There is going to be 0. Our alternative is, if this is 0, then you're going to get homogeneity of degree 2. So if this is also 0, if and only if, then we're going to get. So now let's go inside and take the derivative of this. So we're taking a particular point on the boundary, x0. x0 is z here. So z and x0 is the same thing for me. So you go inside and take the derivative. So when you take the derivative of gradient to power 2, that's going to be exactly this. Agree? So you have gradient of u to power 2. This is it. That's gradient to power 2. Take the derivative, this is the derivative of this, product rule. So it will be 1 derivative plus, that's 2. And then you have the derivative of this guy. Prime here is the derivative. And then minus, you have u r to power 2. Derivative of that is 2 times u r and u r prime. So now you integrate this by parts. So what happens? So this guy here. In order to integrate this by part, what you do, you take this guy, because you have good grip on gradient of UR, but not on the gradient of UR prime. You don't like that. So take this guy, go to the boundary. So if you do that, you go on the boundary, this is what you get. So it will be gradient of this guy times the normal vector on the boundary times the function UR prime, and then it will be a Laplacian of UR times UR prime, minus with the minus sign, and that minus will compensate something. Okay, I'm writing it too compact here, so let me write it for you here. So what you have is equals to, on the boundary of B1, and x times gradient of UR times UR prime. I had a 2 or something before. And then minus Laplacian of UR times UR prime. And then I had plus 2 times UR prime. And then minus the last integral, which is 4 times UR prime on the boundary. This is on the B1, on the boundary of B1, B1 on the boundary. But this guy is characteristic function. So I can just take it out because this is representing the characteristic function here. And I get this one goes with this one. You go together on the boundary, and they go together. Don't I have a 2 here?
Yeah.
I have 2 here. So they cancel. So this is 1 basically. 1 and 0, but this sort of takes care of that. They go. This is what's left. But you see that you can actually rewrite this. That's exactly the derivative I took for you. This is the derivative, the whole thing here is the derivative of UR up to 1R. And then I already have a UR here, UR prime here, so that's going to be UR prime to the power 2. Okay, so take this UR prime here and UR prime here, factor it out. So it's x times gradient of UR minus 2 times UR. That's exactly what I had in this board before. That's UR prime. I get UR prime times UR prime, and bingo, it's not negative. Now, if the function is homogeneous of degree 2, this is 0. That's what we said. If everything is equality here, I haven't changed anything. Everything is equality. The prime goes all the way, becomes this. So if UR is homogeneous of degree 2, the last integral, or actually the integral, is 0. So the integral is 0. It means that W prime is 0. So for homogeneous degree 2 functions, it is 0. It's monotone, strictly monotone. It strictly increases unless it's homogeneous of degree 2. Now you realize that if you have a homogeneous solution, then this will be completely, your W will be completely constant. W prime is 0. So it will be constant. So it tells me somehow the energy levels, but doesn't change. The energy doesn't change. I can use that information a lot. Now think that if you have a free boundary point, now we are in the global setting, the work global setting. So if you have the energy value here, W starts here, it has to become larger and larger or stay constant. So if you have a point when the energy is very large, is infinite, it's a global solution, not infinite, sorry, the largest energy value, then it cannot increase anymore. This is the largest possible value you have if you have a classification. So it means that your solution has to be homogeneous in the polynomial point in that particular case. So these are the things that we will now play around. Okay, this is something that I just show here for you. Homogeneity. Okay. So next step is actually a very important step. So I claim that blow-up solutions, let me go back here. So I claim that blow-up solutions here. If you blow up, it will be homogeneous. Why is it homogeneous? See, now that monotonistic formula can help. Here is the drill. The monotonistic formula tells me that if W is constant, it is going to be homogeneous of degree 2. It means W prime is 0. W prime is 0, it means that U prime R has to be 0. U prime R is 0, it is homogeneous of degree 2. So I take W's at the point 0 plus, so it means I'm going in the limit. So I let R go to 0, there is a value, it is monotone. The monotone function always has a limit. So you start with the value here someplace. It doesn't need to have a value at this point, but there is a limit because it's monotone. So it's monotone, there is a value in the limit. It's equality here. What I do, I take two different parameters, S and R. I let R go to 0, I get this one. This doesn't matter when it goes to 0. And now, instead, I do a scaling. So I can take out R exactly as I did in my previous one. So go to the previous page. Here. You see here, I can rewrite it like this. So think of it as there is an S here, S times R. I can still rewrite it into Born reduced S. So it will be the energy of Rs will be the energy at S of UR. So I scale only with R, not with SR. So I keep S. So if I keep S, scale it with R, this is exactly what we're going to do. So put a mark here. This is an exercise to verify it. So verify that step. It should be elementary verification. So verify this step. And now as R goes to 0, UR converges to U0 for subsequence like this. And we're going to get constant equals to WSU0 with the center 0. What does it mean? It means that that monotonistic function, this monotonistic function for U0, for any S, is constant. So now think instead of S being R, that's what we said. So this is constant, this guy is constant, and then our previous page said strictly positive unless this is 0, homogeneity of U2. So that tells me exactly that U0 has to be homogeneous. There is no other chance. So what I get to is that U0 is homogeneous of degree 2. So a blow up is homogeneous of degree 2. That's the proof. Okay. Now we have to use this and go on further. Now we have a partial classification. So
There, we don't get that U is homogeneous of degree 2, right?
no, not U, but U0.
Yeah, there.
No, U is a local solution.
Yes.
U is a local solution. I'm saying that if I blow it up,
But then
I get homogeneous. No. This doesn't say that global solutions are homogeneous, so even your solution is global to degree. So conclusion is that any blow-up is a homogeneous function of degree 2. Okay, and this is the next step. that any global solution is either a polynomial or one-dimensional solution. So let's see how we prove this. I'm not think definitely I will make the board here, so let me prove this. So our one-dimensional solutions are going to be solutions like this, or rotation of it, any possible rotation. So x times a vector, unit vector nu, and the positive part of that, the power of 2 divided by 2. And so after rotation, I can always see it like this. The problem is that, so still, it doesn't say that different blow-ups gives you the same solution. It just says that all blow-ups are going to be homogeneous. It might be this one, half space, or this one, I don't know. And you already see here that it can rotate all the way. And there is no possibility of seeing that the free boundary is a graph. So let us look at the classification. So here it comes. So I'm looking at two possible scenarios. The set has an empty interior. So U0 equals to 0 as empty interior. That's one possibility. Another possibility is that it has non-void interior. So the interior of that set is not 0. So now you're in an entire space. You have Laplacian of U0 is 1 almost everywhere, if I'm looking at this. Okay, so if it has interior, okay, so here's a question for you actually. So it has interior, so case 1. So U0 is 0. Interior is that. So let's look at this case. So what does it say? I claim this gives that Laplacian of U0 is 1. Can you see why is that? I'm saying that U0 being 0, the coincidence set has interior which is empty. I know it's homogeneous. Okay, that's one case. And I'm claiming that this means that Laplacian of U0 is 1. I know Laplacian of U0 is what? Is Laplacian of U0 is characteristic function of U0 being positive. So it means Laplacian of U0 is going to be 1 everywhere, but on the set when U0 is 0. That set doesn't have interior. Can I just take it out and say my Laplacian is smooth and is 1 everywhere? Why can I do it? Do you remember that free boundary as Lebesgue measures 0? See, now it's become important. The free boundary as Lebesgue measures 0. It has no interior, so Laplacian of U is going to be basically this, and U0 is 0. This is exactly the free boundary. If it has no interior, if U0 is 0, interior is empty. If its interior is empty, if you take a set, if it has no interior, the boundary is itself. So what I get is that that this set is the predominant set. But then this set has zero volume reaction. So measure is zero. Measure is zero, this means that Laplacian of U0 is characteristic function of these one almost everywhere. If Laplacian of U is one almost everywhere, and the W2P functions don't feel the rest almost what is outside almost everywhere, we can just say it's one everywhere. Okay? We can redefine it. One everywhere. Or we use the Wise lemma or classical Wise lemma. Or alternatively, you just say W2P functions. We can take out what is left of almost everywhere, and my Laplacian will be one everywhere. That's it. So, if that is so, then I will get Laplacian of U0 is 1. This is a typo. I should change this at some point. However, this is a typo. I will change it. So remind me to change it. So it means that Laplacian of U0 is 0 almost everywhere, and that's quadratic growth. Okay, this 0 is 1. Maybe I write it in the pen.
No.
Have you seen this movie? And there's a very interesting video. Professor teaches something, and then he says, "Oh no!" And then he takes the pen and starts writing. Oh my God! And then it starts. Somebody else starts helping. So help comes from somebody else, and so internet connection. That's very nice. And then fire goes on. It's a very beautiful movie, actually. It's like 5 minutes, 2 minutes, 3 minutes, something like that. But it's very nicely done. Very high technology behind it, computer technology. That they interact from different places. So it gives it the water. So he takes the water like this from it, and he takes it from outside. Anyway, so let's not digress too much. So this is 1, not 0. And we have quadratic growth. So we can apply a Liouville theorem. This is a good exercise for you. So try to see that from here that you really get the polynomial of U2. So Laplacian of U0 is 1. U0 has quadratic growth. That means that U0 has to be a polynomial of U2. Can you see that directly? Or? How would you do that? Do you know Liouville theorem? Yeah. So you have to use Liouville theorem. Okay, I will leave it. I have the tendency to answer. Okay, good. So that's good. So that's the first case. The second case is a little bit more nasty. So we need to use the more analysis. There's probably lots of other proofs, but when I was writing, this is what came to my mind. Actually, there is another proof I can write away, which is much better, faster. That's the monotonistic formula of ACF. It gives you directly a proof. Maybe I will draw it for you also. Let me do that one first, and then we go to this. Okay, so let me do the proof for the next one with the monotonistic formula, and you'll see the strength of that. So you remember the monotonistic formula from yesterday? That was, so this was 1 over R2, gradient of derivative of u plus power 2 divided by x center origin power n minus 2 over dr. And then the same with the minus here. So instead of plus, you have a minus. For the same thing. This is important. Minus. What we have is that this is monotone. Actually, we have the following. So monotheistic formula tells me that psi prime is actually strictly monotone increasing. So epsilon r positive, where epsilon r somehow depends. I'm writing it in a little bit confused way, but epsilon r depends on how much. Depends on how much. You can actually find epsilon r in one of my papers with Louis Caprari and Larry Carr. There's a computation, and you can find it exactly. It's not important. Important is it's strictly positive. So whenever it's not zero, whenever there's a digression, depends on how much the set EU plus is positive and negative digress from the half spherical cap. So the supports are different, like on the codes. Okay, so this would be intersected with boundary of dr. So you look at the sets. So this is a conic. In our case, it's a conic one. And then you look at the surface of what our radius are. If the set when the function is positive or strictly positive, that sets are going to be different than a complete half spherical cap, two different ones. Then this function psi is strictly monotone. So once it gets little digress from this, it will be something like this. Then it will digress. There will be strict positivity, unless they are like this fit together. If they are fit together, the problem is that may rotate, but I don't care about that. But now I'm saying the interior is not empty. It means that there is no possibility for the support to be two spherical caps, because the interior, there is a cone. They can never be caps, complete half spherical caps. So it means that this is strictly monotone increasing. Okay? But we know that this is not increasing because if it increases with the value, this is a cone. So at each step increases with the value of psi and r. So it means that psi at infinity has to be infinity. It always increases with fixed value. So it will have a linear growth. Let's say epsilon 0 times r, and it goes to infinity, like epsilon 0 r. But I know that my function at infinity is going to be bounded because my function is C1, 1. So the whole thing is bounded, and this integral is always bounded. So I'm going to have, that's the proof of this. That you're going to have really two spherical caps, half-dot spherical caps. So it means that, so what we are remained with is that this scenario is not going to take place. And what can we think of here to use? I will complete the proof. So I'm coming to a contradiction, that this scenario is not to take place if there are cones outside like this. The only chance for this statement to survive is that one of the integrals are 0. If the integrals are if the integrals are not 0, both of them, then it will grow and will be infinite. That's not possible. So it means at least one of these guys is going to go 0. If one of them is 0, let's say this one, and that would go for all directions E, then it means that that you're going to get that this integral here is going to go to 0. is going to be 0. So gradient of DEU is 0. What you're going to get is actually DE, you're going to get that the function U is one dimensional. That's the only chance. Okay, very little to fill out. It's going to be one dimensional. And the one dimensional solution is exactly with no interior, with a non-void interior, it's going to be exactly this one dimensional that I'm telling you about with my previous page. That's one proof of it. But then you need really to go into this deeper analysis, but it's very simple once you have this strict monotonicity and all that. But I'm going to use, but actually this proof works even if you don't have a sign. So this is what we use partly in our problems when you didn't have a sign. But when you have a sign, you can actually do it simpler. When I say simpler, it's a little bit longer, but on the other hand, it doesn't use strong tools. You use simply the geometry. So let's see what's happening. Maybe I use this.
So here, this is proved at that interior point. You want to show this at in the region where.
No, I want to prove that if the interior of the coincidence set is not empty, then it's going to be only possibility that is that it's a plane solution, one-dimensional solution.
No, so this to prove the second derivative.
I want to prove the second derivatives are non-negative.
On that entire set.
Everywhere when it exists.
Okay.
Of course, when it is 0, so it is zero,
Yeah.
so it is not negative. So almost everywhere I will prove this. So of course, the best way is to work inside because on the boundary I don't have much information. So I will prove that this is larger than or equal to 0 inside, and then all since it's also bounded, so all the way to the boundary is like non-negative. So now think. So before I go into the proof of this, so I have a cone. It can be a very nasty cone. So think of what is a cone? Cone, you look on the surface of the unit ball, the boundary of the unit ball, and then you have a bunch of sets, and then you draw the cones. So it can be very nasty. So what I'm saying is that this is going to be only one possibility, and then the function is positive here. It's completely 0. The cone is going to be a half plane. And in order to do that, I will prove convexity of my function. Global solution, I will prove it's convex. So global solution is convex. It means that, two-dimensional, that you cannot have all possibilities. The whole set when U0 is 0 has to be connected. At least connected. So you see that it starts giving you information. Okay. And then you can do this for all directions E. Convexity comes from there. And when you use that, then you can prove that if DE_U0 is non-negative, and now you can think of DE_U0. DE_U0, and then DE of that. So that means that DE_U0 is monotone in direction E. It's monotone in direction E, it becomes 0, so the function is increasing in that direction. And once you do that, then you end up with a scenario that tells you that, okay, you're in trouble unless there's some specific geometry. So I'm going to go slowly through this. Yeah, let me also get this. So when are you supposed to finish 12:30?
12:30, yes.
That's not sure if you can manage through this, but if I do it really faster, I think we can manage. So, well, I gave the proof for this very fast, but you don't need to focus on that. Since u0 is non-negative, I can actually use a different device. So let us start to prove that generally global solutions are homogeneous, are convex. They don't even need to be homogeneous, but because this proof works very general. So I will prove that they are convex. So this is convexity. For any direction E, the pure second derivatives of the function is non-negative. So if the pure second derivative is non-negative, that means convexity. So once you become 0, then you stay 0, and then again you can become non-negative. Like this. It's going to be, so this is convex. So it tells me that u0 is convex. The first thing to remember is that u0 is C11. If u0 is C11, the second derivatives are bounded from above and from below. So this is at least bounded from below. I want to prove that bound is actually 0. That's convexity. So I know that this is always larger than some constant, minus c. I will prove that actually that minimum value must be 0. So I will take the minimizing sequence for my second derivatives. Take a minimizing sequence. So there's a point, the function takes some value, another point, some other value. So I track this minimum value. I don't know where I end up, but I can track. I take infimum of du0x. So that's that called f, and then you have a sequence. So I need pictures now. So here what happens is that if I take, this is xj, and then I take the distance to the boundary. That's dj. So I will take the bulk of radius, dj, center here, and scale it. Here u is positive. Observe that this xj might go to infinity. I don't know that. If it goes to infinity, I don't care. If it goes to the boundary, I don't care. It will never stay inside, because by minimum principle. Because second derivatives of u0 is a harmonic function. If Laplacian of u0 is 1 inside, then any derivative is 0, second derivatives are 0, so it's a harmonic function. So this is a harmonic function. So minimum will never stay inside. It will go either to the boundary or infinity. But if it goes to infinity, I take it back in this way. If it goes to the boundary, I push it away. I push away the boundary. And I will end up with a scenario which is quite favorable to me. And I will have a new scenario. Do I have u0 all the time? Yes. Oh, this is v0 now, yeah? So I call v.
Define beginning.
Define different. Yeah, we define vj to be the escape function. So now I'm looking at vj. So I have v here, sequence. So here, so vj is defined here, and then I always have a free boundary point here. By scaling, I get this one, and this is always the unit ball, which is the center. Vj at 0 is like uj at the point xj, basically divided by the distance. These are bounded. Laplacian is 1, the functions are bounded, vj's are uniformly bounded because it's C11. And that's quadratic growth. That was very important. Now you see that it comes in again, that we need this quadratic growth. So a subsequence will converge again. It will converge, and in the limit, Laplacian of v0 will be 1 in the unit ball and everywhere else, which is in a connected set. So there might be lots of other sets here. I don't see that at this moment. because I don't have any picture of my domain. This is a very nice domain. There are all kinds of holes here and there, I don't know. But I will take that connected set, basically, and work with that. I will take the connected component. So I take this connected component where the origin was. The origin is actually the limit of xj's. I've just translated that. So my function at the origin is like my old function at xj, second derivative set xj, and the limit of that. That's going to be minus f. The value of my function is minus f. Of the second derivative, so b0 is minus f. Minus f is the smallest possible value for this. So smallest possible value for v0, the second derivative of v0, is minus f. And it's taken inside the domain. Minimum principle is violated unless this function is constant. So it means that this function is going to be constant in the connected, only in the connected component. The other components I just throw away. I don't see them. I don't like them. They don't help. So I will get that this is going to be a constant. And then what I can do is integrate. I will integrate in the direction e. So let's say this is direction e or something. Here I'm giving you a simple picture. You can actually take all, again, possibilities of smallest directions, etc. and be a little bit more effective, but let's do it like this. So if the function is like this, of course it can happen also that the direction is based on e's. This is like a plane, and e is in this direction. So all possibilities may appear, so you have to be careful here. But let's not to overdo this, at least not at this stage. So if you rotate this and assume e is e1, you can rotate it, assume e is e1, and then you will have the first derivatives, the second derivatives in direction e1 is constant. Now you can integrate in direction x1. If you integrate, this is what you're going to get. Minus m will be, well, second derivative is minus m, so the function has to be like this, plus something else, which doesn't depend on x1. And I will leave this part to you with a little bit of the geometry here. This is calculus, but this level here in calculus. Prove that this is not going to happen. How do you see that? Do you remember not degeneracy? So we said that supremum of this guy is going to be larger than r squared. But all of a sudden I have minus mx1 to the power 2, negative. So the question is whether this guy is going to help me with the supremum value, and then you have to use that the function is 0 in some sense. It's a homogeneous cone. The volume is positive outside, so you're approaching a set. The function is non-negative itself, so this function has to be non-negative completely. So what happens? Is this possible? So work out the contradiction with that v0 is non-negative. But actually it's easier in this case because we have already a sign here for that. So we already have a sign for v0, so these two do not match. Okay? Because once you are large with x1 and x prime is bounded, then in that direction you're going to get a negative value. That's not going to work. So that's actually easier. But this still works if you don't have this sign condition that you can still control. So okay, so this is a contradiction. So it tells me that I have convexity. So let me see. Okay, so let me try to finish this up. Now set v0 is 0 as non-void interior. So let me see. Why does it have non-void interior?
That's the assumption, right? We started with
Yes, V zero
Start
has
with
it,
the
yes,
second
yes,
case.
yes, that's true. Oh, okay,
Then
now,
that's
yes,
what
now
happens.
we're going back to our original function, V
Yeah,
zero.
yeah.
Going
So we
to,
use zero.
should be U zero. I think I'm still at V zero. Yes,
I think you need
I
to
think
go
we should
to
have,
zero.
we should have U zero.
Yeah, use zero.
Yes, we should have U zero here,
Yeah.
yeah. So it means that, okay, so I have the, yeah, thank you, that's true. So I'm going back to my original function, U zero, and I know that this is non-negative. This is non-negative. Now I've proven that, convexity. If this is non-negative, and it has non-void interior, so there is a place here where it's in a cone, like this. So if this is the direction, E, I take whatever E I can take, is the same. So my function is going to be the derivative. So second, this is non-negative, it means this is non-negative. So it means that this function is increased. Okay? If the derivative of function is non-negative, it's increasing function. So this guy is increasing, that's what I'm writing there. And you start from here, so it increases. And I want to get negativity, so how do I get that? Yeah, I will take it's increasing, I will take this direction also. So it means that this is going to increase. Okay? I'm losing something here. Yes, okay. So I take a volume here. Function is zero, so it means that in this direction it has to decrease. So
That would be just your PD
we're trying
maximum
to
raising.
prove that this is going to be,
In the outward direction, it is going to be decreasing, right? Because on the it's Laplacian of u naught is
I
greater
think
than
I'm
zero.
still at the level of V0. Let me see, I even lost myself here. Let me go back. There's too much text, I should have written it differently. So I get V0, which makes negative values and contradicts V0, so okay. That this is decreasing. Let me go to the next page, see what I'm getting at. Okay, mute. I think I'm overdoing this. I think I'm overdoing it. I don't need all this. Thank you. Let me come back to this in afternoon.
Yes.
I feel a little bit exhausted. So I'll come back to this in afternoon. I think I'm overdoing it.
Yeah, because we have to go back to u, right?
Yes, I think I'm overdoing this. I think I'm overdoing this. I don't need all this. So let's come back to this after lunch. I'll be refreshed. Yeah, I think I'm overdoing it. I'm okay with all these arguments. No, not afternoon, tomorrow, yes?
Tomorrow, yeah.
Yes.
Because
Yeah.
after this, maybe you just go back to u naught, and then you maybe want to show that u naught is
So what we have to-
from x
Yeah,
plus.
let's do it now because I don't want to wait until tomorrow. So
No, you can repeat tomorrow.
okay, let's do it now. Yeah, okay, let's do it tomorrow.
Yeah, I agree. It is because it's till here it is fine. No, till the previous.
Yes.
Till the previous page
I don't
it
see
is fine.
where's this page is coming from. Somebody
No, I
went
think
to
it
my
should
files
be.
or
I think it should be u0 there because.
no, that's V0. That's V0. That's correct.
This one is fine. Because you already got a contradiction to v0 greater than equal to 0, right? And you want to
I have a contradiction, so that means that that u0 is counted.
Yes, you have second derivative because you started with a contradiction to that, right? So d second derivative of
Yeah, this
u0.
contradicts this one, so
You
I
are
don't-
also all this here should be u0. That's
all
what
this should be u0.
Okay,
But
so-
still, I don't need this.
No, you want to
No,
show
I
it is
don't
of
need
that.
this.
No, you want to show it is of the form x plus 1 square. Maybe that's why you
I think this is what happens. Now I think I know what happens. Is that all of a sudden I switch to the case when the function might also have negative values or something like that. I'm trying to do that too, but we don't need that. So now it's nice. So we don't need really this stage. This is used when the function is also
sign changing.
positive sign changing or something. So we don't need this. Now we say we use convexity.
Yeah, so this is
That blow-ups are one. So we use that to prove blow-ups are one-dimensional, and then that's it. I switched to B0.
Yeah, I think so. It should be u0 here.
I should change it.
Yeah, it should be u0 here.
I went through this with some.
In the previous slide, it should be u0 then.
Yeah, but I don't need that slide.
Yeah, you don't need that
because it's
for
already
sign
set.
changing.
I'm just repeating myself.
Yeah.
So this will tell me that yes. So if I get this, it means that this function is okay. So here's the argument for you, which will be tomorrow. I will repeat this tomorrow. But this is an exercise for you. It's a calculus exercise again. I'm saying calculus all the time. And you think, what is it talking about? So suppose you have a two-dimensional function. No PDEs. It can be n-dimensional, but let's do it in two. So exercise. You have function f depending on x1 and x2. No PDE. Calculus 2. Suppose for any direction, DEF is non-negative. For all directions. Suppose the function is monotone in all directions. Prove this function is one-dimensional. It's one dimension.
And that's everywhere, right? On the whole of Rn.
In the entire space.
R2.
You should be able to prove this. It's calculus 2. Okay, so let's go for lunch and then just we go through a little bit practicing exercise in the course with Margaret.